All right, let's just jump right in and move past all that cryptocurrency hype, okay? In this explainer, we're going to treat blockchain as what it truly is, a highly restrictive but absolutely fascinating software component. We've got a research-backed blueprint to share showing you exactly how to build with this tech by mapping out real architectural design patterns for blockchain-based applications.
So, here's the million-dollar question. We all know blockchain is famous for crypto, but how do developers practically integrate this decentralized technology into real-world, enterprise-level systems? I mean, sure, it offers bulletproof data integrity, but it comes with some pretty severe handcuffs when we're talking about privacy and performance. To figure this out, we're going to unpack 4 distinct design patterns today: the Blockchain Architecture Challenge, Bridging the Walled Garden, Binding Law to Code, and finally, Securing the Public Ledger.
Let's start right off with Section 1, the Blockchain Architecture Challenge. Before we can start breaking the rules, we have to quickly trace how data actually hits the ledger. It's a journey. First, a data package is created, then it's signed by its owner using a private key. After that, it gets validated by a receiving node using strict algorithmic rules, propagated across the entire network via gossip protocol, and finally, it's verified and mined into a block through a consensus protocol.
And this structure perfectly illustrates our baseline. You've got the chained data structure, and you've got the decentralized network. Nodes are reaching a consensus on data without ever trusting a central integration point. There's literally no central server in the middle pulling the strings. The whole shebang is entirely peer-to-peer.
Which brings us to the real engine of second-generation blockchains, the smart contract. Now, while this is an incredibly powerful programmable infrastructure, we have to remember these are pure functions by design. They're totally isolated. That means they cannot natively access the outside world or external systems at all.
So, as a software architect, you're faced with this stark, glaring contrast. On one side, you have the perfect, self-contained vault of the immutable blockchain ledger. But on the other, you've got the messy, constantly shifting realities of external enterprise systems. If we're going to build anything useful, we have to somehow bridge that gap.
Which leads us perfectly into Section 2, Bridging the Walled Garden.
Since these smart contracts are effectively blind to external conditions, we have to ask a pretty basic question. How on earth can a smart contract know the weather, or geolocation, or who won a sports match last night? If it can't just ping a web API directly, how is it supposed to execute business logic based on real-world events?
Well, we can actually solve this in 2 different ways. First, there's the Oracle pattern. This is where trusted external components pull facts in and inject validation results straight into the blockchain. But on the flip side, we have the reverse Oracle pattern. This one allows massive off-chain legacy systems to query the blockchain, verifying data without having to tear down and overhaul their own core infrastructure.
To inject those external facts, developers rely on trusted third parties, and these can really vary. They range from centralized oracles, which might just be a single external server, all the way to distributed oracles like Orisi, where multiple independent servers actually have to agree using a multi-signature setup. You could even use decentralized prediction markets like Gnosis, letting users pick an arbitrator they mutually trust.
Conversely, look at projects like Identity, which enriches banking payments by embedding identity tokens into the SWIFT protocol, or Slock.it, which manages autonomous IoT devices. They use reverse oracles. They get all the secure validation benefits of the blockchain without having to redesign their massive existing off-chain systems from scratch.
All right, moving right along to Section 3, Binding Law to Code.
So how do we actually digitize complex legal terms? We use a pattern that acts as a secure digital handshake between a lawyer's natural prose and a developer's executable logic. It establishes a bidirectional binding, essentially making the smart contract the absolute authoritative source of the legal agreement. Think about the mechanics of that handshake. The physical off-chain agreement explicitly writes out the smart contract's address. Meanwhile, the on-chain smart contract is specifically programmed to store the cryptographic hash of that exact legal text. It locks them together in a strict one-to-one mapping. And this pattern is just absolutely crucial for modern enterprises. It automates regulatory compliance, triggers conditional payments, and provides a permanent, completely immutable audit trail. In fact, it's already being pioneered right now by platforms like OpenLaw on Ethereum, and it's supporting smart contract templates explored by huge financial institutions like Barclays on the Corda blockchain.
Finally, let's tackle Section 4, Securing the Public Ledger.
Here is the elephant in the room. On a public blockchain, there are no privileged users. None.
Any confidential data is out there, exposed to everyone. To solve this, systems like Hawk or Oracle Eyes use a pattern called encrypting on-chain data. This lets participants encrypt sensitive parameters locally before they ever hit the chain, basically keeping trade secrets completely hidden from the public.
But, and this is a big but, doing this introduces a massive off-chain dependency. Because you obviously can't share a secret key across a totally transparent blockchain, right? So now you have to flawlessly manage the generation, exchange, and storage of all those encryption keys entirely off-chain among your participants. And honestly, this brings some severe, potentially catastrophic drawbacks. If a key is ever lost or compromised, boom, all that data is exposed. Plus, access revocation is practically impossible. If someone has the key today, they can read that immutable data forever. But the scariest part? Because that encrypted data sits permanently on a public ledger, it is sitting there highly susceptible to future tech leaps. I'm talking about quantum computing, which could retroactively crack our current encryption algorithms down the line.
Ultimately, as the researchers point out, blockchain just isn't a standalone magic bullet. It's really just one part of a much bigger system, requiring very careful, pattern-based integration to work securely alongside your off-chain databases and legacy APIs.
So before you rush to deploy anything to a decentralized ledger today, you really need to ask yourself this one critical question. If your data is recorded immutably forever, is your current encryption truly future-proof? Definitely keep that in mind the next time you consider putting a permanent trade secret out onto a public chain.